And we are live. Welcome, everyone. My name is Britt, and I'm the marketing manager at Eatron Technologies. We're very excited that you're here with us today for our 9th Talk to an Expert. We are live every last Thursday of each calendar month at 4 p.m. UK time, so please keep your agendas open. If you miss any one of them, they're also on Spotify and on YouTube and on our website, or you can watch them back on LinkedIn as well. So for those who don't know us, Eatron is an international technology scale-up. We are dedicated to making software-defined vehicles a reality for OEMs worldwide. Our house rules are, if you have any questions, please put them in the chat whenever you feel like it, so that today's expert can answer them at the very end. So we have Ivan today, who is our technical specialist of software and controls. Hi, could you tell us a bit more about yourself, please?
Hi, Britt, and hi everybody who joined this Talk to the Expert session, a webinar. Nice to meet you all. So, as Britt said, my name is Ivan Zajic, and I'm technical specialist here in Eatron Technologies, and I'm really glad to be here and actually speak about state of charge today. In the past, I was a lecturer at Coventry University here in England for about 10 years, full time and then also part time. And I was lecturing specifically system identification, mathematical modeling, control theory, and adaptive control. And all of that just came handy when it comes to battery management systems and state of charge estimation, specifically for today. And then also my industrial career, I have 6 years of experience of developing from in a research environment up to production environment. I have experience with 12-volt lithium batteries, 12-volt lead acid batteries, up to high voltage lithium batteries. And my specialty is really developing all these state estimators and predictors and all these, for me, fun stuff, and hopefully to you practitioners as well. Thank you, Britt.
Thank you. Well, let's dive straight into it as we're doing a deep talk today. Could you please define for us state of charge?
Thank you. That's a very good question. That's a very good question, and I just can't answer it just like that, you know. And I prepare a small presentation for us.
Okay.
To apologize beforehand. There'll be some graph and equation. Let me share my screen with you. Share screen. So which screen is going to share? This one. Perfect. Share now. And this. You should see it now.
Yes.
Perfect. Perfect. So to define, so state of charge really is the energy level in your battery. But before I can even describe what state of charge is or what people think it is, I have to actually define what charge is. What charge is. I know, but I'm not sure what at what level the audience today is. So I just want to make sure we are all on the same page. So charge, the unit of electric charge, is a coulomb. It's named after French physicist Charles de Coulomb. And the more common, but in battery industry and in automotive industry, a more common measure really is ampere hours. And one coulomb is 1 ampere second, and 1 hour has 3,600 seconds. So that is the unit, ampere hours. And then the battery capacity is the amount of charge, you can squeeze in. And it is the charge you can draw out from full charge battery until it's empty. And just by the unit definition, you can actually see how it is calculated. So it is ampere, so current you are drawing from battery multiplied by time. If the current is changing over time, it makes sense to integrate the current. And of course, we work with embedded control systems and then computers. It might be discrete, really. So we have some discrete integral here. And to really To really help you to understand what capacity is, I have prepared some graphs here. Those are real measurements from a real cell. This is a 12-volt lithium-ion battery, because Eatron is in collaboration with an amazing battery manufacturer, and these are somewhat scaled data, so that it's not entirely the real deal, but it's exactly how it is. This is 60 ampere hour battery, and let me just explain how capacity will be measured in practice. This top left graph is showing to you battery voltage, and we fully charge the battery first, and then we are drawing out the current, we are depleting the battery until its voltage will collapse and will hit a predefined cutoff voltage, a threshold. In this case, 10.5 volt. That's a common threshold for 12 batteries in automotive industry. And on this graph, you can see the current being drawn. It is 12 volt in this case. And if we are multiplying 12 multiplied by 5 hours, that gives us 60. And in real time here, we can be calculating this integral and seeing how much ampere hours we are discharging until we discharge 60. The matter can get even more complex if we imagine the battery is then cooled down maybe to minus 15 degrees Celsius here. Again, we are discharging the battery, but this time the battery voltage collapses earlier. It's because the battery resistance is higher. You are drawing current, there is bigger voltage drop, and you hit that voltage threshold earlier. And because of that, we were only able to extract 50 ampere hours, not full 60. We can also plot the voltage against the charge drawn out of it. And we can see that we were only able to deplete the battery down to maybe 10 ampere hours. And then the batteries I usually work with here in Eatron, there'll be 12-volt starter batteries, 12-volt lithium-ion power-net batteries used in electric cars, and the capacities would range from maybe 30 ampere hours to 90. Then in your vehicle, if you have a mild hybrid vehicle, you would find a 48-volt battery, be from 8 to 20 ampere hours. And then in a battery electric vehicle, that the traction battery, the 400-volt battery, that will be somewhere between 100 to 300 ampere hours. So you can see they're all similar sizes, 12-volt battery, 90, 400 volt, also starting at 100. So that is the capacity. So now let's have a look what the state of charge is and how practitioner could actually benefit from that. So in control engineering and state estimation, there are no fixed definition. This is not there are no ISO, there are no standards as such. But the kind of common definition is that it is the percentage of remaining or residual charge to maximum available nominal capacity. So residual charge, how much more can I draw, divide by nominal capacity. In our case, it was 60 ampere hours. So this denominator, we already know how to measure it, how to obtain it, and what it is. But how about this numerator? How about the residual charge? So while the above equation is true and people understand it, there is commonly a confusion about the definition of residual charge. And I can see it about amongst colleagues and amongst customers, and I can see it, people are not fully sure what it is. And so perhaps let me show you an example what that residual charge is and why is it important. This is the same graph as from previous page, but now I have added just one more capacity measurement, slightly different one. Let me take you through it. Battery is warm, 25 degrees Celsius. We fully charge it, so it's fully charged now, and therefore the residual charge is 60 ampere hours. 60 divided by 60 is 100%. Battery is charged. Perfect. We understand 100%. But then we decide to deplete the battery and we remove 36 ampere hours. And that's how this red curve moves to this blue curve. We are now at 60 minus 36 is 24. We are now at 24 ampere hours there. And so, by definition, the battery has 40% state of charge. That is its energy level, its absolute energy level. The battery really contains 24 ampere hours, 40%. And then we cool down the battery to minus 15. These are real measured data, by the way, real measured data. We cool down the battery and we start discharging the battery until it hits the cutoff voltage of 10.5 volts. However, the residual charge we were able to remove is only 15 ampere hours. And 15 divided by 60 is 25. So those 25% I would call available energy rather than absolute energy. So if you ask me what state of charge is, I would say it is the absolute energy level in a battery, and it is a job of state of charge estimator to obtain that. If you ask me how much of available energy there is, it is a job for some energy predictor, state of energy estimation. In this scenario, we can see that the temperature has caused that there is less of available energy, but also, surprisingly, the blue and black line, they start at minus 15 degrees Celsius, but they don't end the same. If you start discharging battery at lower SOC, you are able to extract a little bit more of energy than if you start at fully charged. So the estimation of available energy is a different topic, and hopefully next time I will be able to explain to interested practitioners. And then very other useful measure of a state of charge used in industry is to link the energy content of the battery to its voltage, specifically voltage at rest, open circuit voltage. This is very useful for chemistries like NMC, lithium ferrophosphate, and LTO. And let me just show you how would you as a practitioner could obtain such curve. So it starts with a capacity test. The state of charge definition, the OCV curve, it's all linked to our original capacity test of 60 ampere hours. So we have done capacity test. We have then fully charged the battery, and maybe we divide it by 100 points. So 60 by 100 is 0.6 ampere hours, right? We deplete 0.6 ampere hours, we rest, and we measure cell voltage. We again deplete 0.6 ampere hours, we rest, we measure voltage, and we repeat this 100 times until we go from fully charged battery down to discharge. We obtain the blue curve, and then we repeat the same when charging. And we repeat discharge OCV and charge OCV. The difference between them is called hysteresis. Unfortunately, it exists. But this curve uniquely links the battery energy to its voltage, and that is what I would say is state of charge. It's not energy predictor; it's absolute energy content linked to its voltage grid. I hope I answered your question.
Yeah, no, you did. I hope the audience is happy with your answer because you went really in depth. Thank you. So could you tell me how you estimate it in practice?
Right. So as a practitioner in industry, well, I prepare another slide for that. Again, I apologize. But no, this time, sorry, some slides skipped. But this time down, not many equations. I promise. So in industry, kind of two popular branches would be column counting methods and state observer-based methods. Of course, in literature we see much more, but it doesn't mean that necessarily they are applicable industry or easy to be applicable on a real vehicles and real applications, because there's a difference between theory and really what we use in practice. I think both methods, in fact, are similarly complex. Let me introduce you the column counting method. It really comes from the definition itself. So let's imagine depth of discharge. It's slightly different to state of charge. When state of charge is 100%, battery is fully charged, depth of discharge is 0. And when we deplete the battery, State of discharge is 100% and state of charge is 0. They are just reciprocal values of each other. And we can take the equation, we can break it down and think about how we implement it on a computer, really. And I would say test of discharge at sample index now equals the previous one plus little new increment of charge coming in. Notice you need to know the capacity of your battery again, the nominal capacity. You must know that. And so there are several design considerations. So one of them, the current, which are integrating, it must include everything. So not just the current flowing to your battery, but also the cell's self-discharge, leakage, current sensor measurement bias. There could be parasitic loads which are draining your battery but are not measured by your BMS, battery management system. And so it becomes, this method seems simple at first, but when you really need to implement in industry, it becomes complex because of all the considerations you must make. You also need to know the battery capacity, and obviously its accuracy directly projects into the accuracy for SOC. You must know your initial value from which you start column counting, which is again not simple. And then the other considerations, let's say you would like to be sampling very rapidly. And based on those design constraints, I would recommend methods like this to be used for stationary batteries or power net batteries, which are often fully charged. So we can estimate nicely depth of discharge. But this method is not standalone. You need some other algorithms around it, which is not often talked about. But for example, you need to detect the battery is fully charged. But in practice, batteries get never fully charged. So what do you do about that? So how to initialize this scheme? The other alternative, which every practitioner should know quite well, is some state observer design. And these methods are inherently estimating the battery OCV. So while the first one is just really counting the charge coming in and out, the other method is just trying to estimate the OCV itself. And then having the SOC OCV characteristic curve, we can judge on the SOC level itself, on the energy content. And again, I would warmly recommend to our practitioners extended Kalman filter methods. I would recommend them. And you can go for full observer design or even just a steady state solution, depending on your application, to simplify maybe a computational load. But also the practitioner should not forget about to make the implementation of such methods to be numerically robust and efficient, which is again kind of niche knowledge. And when you're designing it, there are several considerations to be made, as usually. One would be it's a model-based method. So the quality of the battery model must be there. And equally, I would say other 50% of the job is tuning of that Kalman filter. Ideally, it's adaptive, it's reflecting on model quality, on your measurement device quality. It may reflect on your system requirements, speed of convergence, and the target application. Again, that's not easy, and people usually lack that knowledge, or they think it can be skipped, but it cannot, unfortunately. And I would recommend method like this for high voltage traction batteries, which usually have steep OCV curves. So that is what I would recommend. And then this is of course estimation at maybe at cell level, but in practice, people have whole battery packs where they would connect single cells in series connection to build up the battery voltage. And then again, usually questions are, well, I'd like a battery level SOC. So now we must somehow make a judgment about that. And there is no unique answers. You can imagine there are no almost rules. So it's about the system needs. And I would say that for charging scenarios, your battery pack should be the maximum cell charge. For this charging scenario, we should select the cell with lowest SOC as our battery pack, my recommendation. Me personally, anytime I can, I would select a combination of both, some kind of weighted average. For example, equations like this do that. So when you have two cells, when you are nearly fully charged, this equation will calculate the battery pack to be nearly the maximally charged cell until it becomes that maximally charged cell. For this charging scenario at low SOC, it automatically leans towards the cell with the lowest charge. And yeah, Britt. So I would say that this is how I would estimate SOC for a cell, and then to combine it to battery pack. Thank you for your question.
Thank you. My last question would be, how do you measure the accuracy of SOC?
Oh gosh, don't let me start on that. I think we are out of time now. But I had a slide on that. Yes, it's a short one. It's a short one, I promise. So the evaluation of accuracy really needs to come from its definition. So I have defined two ways. One is the column counting method, and other is the OCV method. Both of them measure the absolute energy content of a cell. So the column counting method, you really need to fully charge the battery. Once you fully charge it, from that moment, you can be calculating your depth of discharge. That is definitely the correct way to estimate a reference SOC. The only complication is that to calculate our DOD, you must know the cell capacity. So that's a kind of noise factor. So as long as you know your cell capacity, this column counting is a brilliant way how to assess SOC accuracy. If you don't know your capacity, your second best bet is the OCV curve. So let the battery to go to rest, measure the OCV, and make a judgment about SOC. But again, there is also an issue. I mentioned the hysteresis, that you need to know which OCV curve you are using, the discharge OCV or charge OCV, or to be somewhere in between. And therefore, you must consider prehistory of the battery, whether it was being charged or discharged, before you can make a judgment about SOC accuracy. Then, oh yes, so it's the last slide. Thank you very much, Britt.
Thank you. So thank you so much for answering all these questions. I already see a couple of questions in the chat from Eatronians, actually, who are very interested in this talk. In what situations would you recommend using state of charge of the battery, and when would you use battery energy estimate?
Right. Actually, I got questions like this from our customers because they also want to know. So the SOC as a absolute energy estimator, I would definitely recommend to use it for control purposes. So anytime you would like to control the energy content of a battery, use the SOC. Also, you need to know SOC to become an input to a state of health estimation strategy or energy predictor itself. Then the energy predictor, I would recommend to use anytime you are interested in what is the available energy content to you. That's especially useful when you are doing driving range predictions, for example, or you simply want to know how much of energy you have right now at this temperature and at this present initial state of charge. So that would be my answer, really.
Cool, thank you. Harry's asking, what kind of SOC accuracy can I expect when using mentioned column counting methods versus Kalman filtering methods?
Okay, well, thank you, Harry. It's a cheeky question. So I think the column counting method, it can be very accurate as long as you know your battery capacity. You know your battery capacity, you may fully charge the battery, you can initialize your column counting, and at that moment, your column counting is the most accurate method on the world. But then as you keep using the battery, over a period of time, it becoming less and less accurate because you have all these noise factors like measurement noise, bias, parasitic loads. And then, as I indicated before, you need other methods to maybe make judgment on how inaccurate you are. The Kalman filtering methods especially on traction battery, if I were a customer of Eatron or anybody, I would simply ask at like plus minus 1%, and definitely it's achievable. And then, yeah, 1%, but the column counting method can be really accurate, but then it just become inaccurate over time. So that will be my answer to you, Harry.
Cool.
Thank you.
Thank you. As we try to kind of keep it short, we kind of cut a few questions, but I'll ask you another one.
Okay.
I would like the SoC to remain accurate over the lifetime of the battery. What are the design considerations and what can be done?
Oh, okay. Well, that's a good one. So, as you know, let's say if you choose to use Kalman filter based method, it's a model based method. So you need to have a model of your battery. And these models are commonly obtained at the beginning of life of the battery. As the battery ages, its quantitative behavior changes over the lifetime. And if you would like your SOC to remain accurate, you need your fundamentals to remain accurate. The battery model, the battery capacity. So you need to adapt those over the lifetime. And then again, I would recommend to always couple SOC estimation with SOH estimation, state of health, and they are feeding to each other. One of the advantages of Kalman filter as such, that is, it adapts by voltage measurement, by voltage feedback. So even if you don't know your capacity exactly, it will provide you still good accuracy, even if it doesn't, even if it doesn't have adapted aged capacity. Maybe it's not anymore 1% accurate, but to my experience, it may become plus minus 3% inaccurate if you don't have state of health. So that will be my answer to you, Harry. So either just don't worry, but accept the less accuracy, or use state of health. Yeah, estimation.
Thank you. Well, I guess we've covered all the questions. If you're listening and you're thinking of another question, put it in the chat and Ivan will probably answer them in the comments.
Yeah.
So thank you everyone for joining. There will be a part 2 if you're interested so that Ivan can come back. And
I think that the part 2, I think I saw interest in people wanted to discuss state of health or alternatively state of energy predictors. So we will see what it will be at the end. Yeah.
cool. Thank you. Well, thank you everyone for tuning in, and I hope to see you in the next one. Have
Thank
a
you.
nice day. Bye.
Bye.